Hello everyone. We are very appreciated to give a presentation on USENIX ATC 2025. Our work is STORM Multipath QUIC scheduler for quick streaming media transport under unstable mobile networks. Nowadays, people are spending more and more time on mobile device. The mobile device include many kind of equipments like smartphone, autonomous vehicles, UAVs, VR/MR device, and so on. A large number of emerging stream media-based usage scenarios, such as video conference, VR/MR, teleoperated driving, and cloud gaming, are running on this device. This application needs high network bandwidth support. It motivates the development of multipath transport techniques. However, it imposes a more stringent user experience requirements because viewers are less tolerant of slow response speed. Besides improving throughput, the transport latency should also be considered. Mobile devices don't stay put. The user might be walking, riding a vehicle, or on a highway. Every handover between base station or weak Wi-Fi spot makes the signal jump, so the link quality can change in an instant. What's more, sync of video. Lose one iframe and the whole group of picture is wasted, but dropping a pframe is often okay. Multipath QUIC let us send those iframes reliably while relaxing reliability for the less critical packets, keeping latency low without risking key data. Motivated by those recent trends, we evaluate MPQuIC's impact on user experience using the Xiaomi 12 Pro under LTE, 5G, and Wi-Fi networks. Surprisingly, we find that user experience was severely degraded with multipath enabled. Specifically, we studied typical experience metrics, including the frame rate, FPS, and the per frame end-to-end latency of video conference. Due to limited LTE bandwidth, single-pass transmission caused frame rate to drop to 13 FPS. Enabling multipath raised all frame rates about 29 FPS, showing its effectiveness for bandwidth-intensive application. Mobility-induced signal variation can make multipath counterproductive. 5G plus Wi-Fi reduced frame rate by 18.4% versus 5G alone, and in the worst case, dropped to 10 FPS versus 25 FPS with 5G, while 92.3% of multipath delays stay below 100 milliseconds. Mobility pushed tail latency to 4.5 seconds, disrupting real-time communication. Further evaluation was conducted to understand the root cause of these user experience degradations. We analyzed signal strength using RSRP, SINR, and RSSI from the OS API. As figure shows, signal strength varies significantly during mobility. The figure below shows that as RSSI decreases, packet loss increased significantly, often exceed 16% at -80 dBm, leading to a frequent retransmission that consumes bandwidth and degrades transmission efficiency. Our log analysis indicates that multipath scheduler select and schedule according to the path, bandwidth, and RTT obtained by the congestion control mechanism. It cannot respond to this rapid change. If a keyframe is late, every dependent frame stalls and the video freezes. MPQuick tried to fix this by sending keyframe reliably and everything else unreliably. That cuts the median delay by about quarter, but the worst packet delay is still 1.6 times slower than the baseline. The reason for this is that a burst loss forces massive keyframe retransmission. Meanwhile, unreliable packet piled up and then forward the link, blocking the next keyframe. Posing unreliable traffic whenever a keyframe is pending, as in case 3 on the right figure, dramatically reduces waiting time and underscores the need for a scheduler that jointly manages both streams. In order to address two root causes mentioned above, this paper proposes STORM. STORM aims to ensure low latency when the multipaths suffer unstable networks. To realize STORM, we maintain two core components: a signal watermark mechanism (SWM) and a reliability-aware shadowing (RAS) strategy, which is integrated by STORM's workflow, a feedback flow and a shadowing flow that together form a unified shadowing system connecting SWM and RAS. As analyzed, link outstage, joint device movement, and the sender scheduler unawareness result in a vicious circle of packet loss and retransmission. This phenomenon motivates us to propose a memory watermark-like mechanism for the mobile device MPQuick. SWM quantify past signal strength, compare it against predefined watermark, and then send differentiated feedback based on the results. To enable the sender to fully utilize SWM feedback, a new shadowing scheme must be devised. We proposed RAS. RAS distinguishes the two traffic classes. It organizes reliable data as blocks, streams unreliable data, and manages the deactivation and the reactivation of paths as their signal fluctuates. The evaluation are performed from two aspects. In controlled network environment, the evaluation focuses on three main aspects: micro benchmarks, the performance effects of individual designs, and the performance effects of parameter setting. Furthermore, we developed three apps for typical scenario: video conference, low latency live streaming, and 360-degree video. These applications were evaluated in real-world mobile internet environments, and the QoE was analyzed. We first evaluate Storm's performance under bandwidth fluctuations using various combinations denoted in megabits per second. The completion rate is the ratio of packets successfully delivered before the deadline to the total number of packets. As shown in the figure, we can see both completion rate and waiting time are improved. The bandwidth combination of 5 megabits per second, 10 megabits per second, both DAMS and MPQuick near reach zero. Storm's completion rate only decreased by an average of 49.3%. In the middle figure, the top of each color bar marks the maximum waiting time for the corresponding bandwidth combination. As bandwidth decreases, the maximum waiting time for MPQuick and DAMS increased significantly by 44.3 times and 54.5 times, respectively. In the worst case, the time reached 11 seconds. In contrast, Storm performed better. For example, with the 5 megabits per second, 10 megabits per second bandwidth combination, Storm's maximum waiting time is 49.6% of MPQuick's and 45.3% of DAMS. Under RTT variation test, Storm delivered the highest completion rate, beating MPQuick and DAMS by roughly 37% at the 30 milliseconds, 120 millisecond pairing. We verify that delayed signal reports don't ruin our feedback loop. Previous work shows that the OS can lag by about 200 milliseconds. In our case, the capture versus actual signal differed by barely 1% on average, and even at highway speed, Storm react within 300 milliseconds. So, special drift is negligible. The control loops stay aligned. Next, we ask how much each component really matters. Without the signal watermark mechanism, throughput dropped 27% and rebuffering shoot out almost 7-fold. Without reliability-aware scheduling, throughput fell 16% and Storm tripled. Only the full SWM plus RS design delivers the smooth experience. Next, let me show how Storm reacts to its two main parameters. First is alpha in our scheduling equation. Think of alpha like a knob. Turn it one way to send the most urgent packet right away. Turn it the other way to keep important data first. As we change alpha from 0 to 1, the delay keeps going down. but the number of dropped frames goes up because some key dates get pushed back. The best point is right in the middle. When alpha is 0.5, we get a good balance, low delay, and still smooth video. Second is how SWMs issue recovery feedback. If we update faster than 100 milliseconds, we create a feedback storm and jitter. Slower than about 800 milliseconds, the information is stored and latency goes up. The sweet spot is 500 milliseconds, and we lengthen it a bit when the device moving more fast. We run 3 apps while the phone move in and out of Wi-Fi and 5G converged. DAMS and MPQuick both lose speed and stall when links drop. Storm keys almost every frame above smooth motion line, which is 24 FPS, cutting low FPS events by about 95% and stall time by over 80% versus the other. Even on 360-degree clips, even on 360-degree video, Stone add roughly 8% more visual quality than the unurgent version, giving the best user experience of all seen. In this section, we look at how Storm boosts transport layer performance in real apps. When links dropped, MPQuick R and DAMSR join in retransmission. But Storm sensed the outage, shut the bad path, and cut retransmission to 1.5%. That same quick reaction slashed 99th percentile packet delay by about 98%. Here is our conclusion of our work. The problem is failure to sense sudden signal change combined with the metro blockage introduced by reliability agnostic shading increased latency. The user experience degraded when suffering unstable network. Our key insight is to leverage signal quality feedback. It schedules traffic with differentiated reliability to achieve lower latency. Finally, Storm can reduce tail packet delay by 98.2% and improve the frame rate of stream media data by 1.95 times when under unstable networks compared to the state-of-the-art solutions. Thanks. If there are any questions, please don't hesitate to contact us.